Now we want to talk about the least squares problem in the QR decomposition, which the QR decomposition basically plays the same role with regard to least squares as the LU decomposition does with regard to solving linear systems. Least squares problem is basically where we would like to find a solution of AX equals B, but there is no solution, so we want to find the X which makes AX as close to B as possible in the 2 norm. Usually, but not always, A has a lot more rows than columns, so that we have too many equations with too few variables. We can't find a solution at all normally, so we find the closest thing we can to a solution. And in fact, there's a very easy way to solve such systems. If you have AX that you would like to be equal to B, all in the world you need to do is multiply both sides by A transpose, and A transpose A then will be a square system, the square matrix, and A transpose AX equals A transpose B will always have at least one solution, maybe many, and if the columns of A are linearly independent, then A transpose AX equals A transpose B will have a unique solution. So basically, the problem seems extremely simple. All you have to do is multiply both sides of your system by A transpose, solve the resulting square system, and there you are. If it has more than one solution, it will always have some solutions, even if A transpose A is singular. If it has more than one solution, any of them will be a least squares solution. So it seems like you should be through with the problem. The only catch is that the new system, after you multiply by A transpose, has the square of the condition number of the previous system, which basically means that it's a lot more susceptible to round-off error problems. But nevertheless, it's still, unless you're really worried about round-off error problems, simply multiplying both sides by A transpose and solving the resulting square system is a perfectly natural way of solving linear least squares problems, and that's what's done many times. But the alternative, which doesn't have the problems with ill conditioning with round-off error, is basically orthogonal reduction. And we're going to discuss that now, the rest of the video. And as I said, the only advantage to this, it's more complicated. They're about comparable as far as computer time. The only advantage of the more complicated approach is numerical stability, less round-off error problems. And if you're not concerned about that, using high precision and well-conditioned original system, then go with the A transpose A solution, the normal equations. But anyway, we're going to talk about the alternative reduction to upper triangular form using orthogonal matrices. Okay, let's look at the following linear system, which has been reduced to row echelon form. We started out with more equations than unknowns. Looks like there's 14 equations and only 12 unknowns. And let's suppose we're trying, and it doesn't have a solution at all. We're trying to find a least squares solution. Now, if you could reduce it to row echelon form, as shown here, the p's are non-zero pivots, the x's are not necessarily zero elements. Once you reduce it to this form, the least squares solution is obvious. Why? Because the last 8 equations that have all zeros in the A matrix, the norm of AX minus B, well, if you look at the last 8 components of AX minus B, it doesn't matter what X is, it's just going to be minus B, and so you basically have no control over the that part of the residual, which you're trying to minimize the residual AX minus B, and it doesn't matter what X is, you're going to get exactly the same in the last 8 components of the vector AX minus B. So you might as well choose your X to satisfy the first 6 equations exactly and make that error 0, and that will obviously be the least squares solution. And so once you have it in row echelon form, it's trivial to find the least squares solution. You just forget about the rows you can't change and solve the ones you can. However, the catch here is that if you reduce your original system AX equals B down to this form using elementary matrices, that is normal Gauss elimination, there's no guarantee that that doesn't change the least squares solution. In other words, the least squares solution of this final reduced form may not be the least squares solution of the original AX equals B, and in fact normally won't be. However, if you, instead of using elementary matrices, the M matrices, to reduce this to upper triangular form, if you use orthogonal matrices, then it is guaranteed that the least squares solution won't change, and that's pretty easy to prove. In fact, here's the proof. If you multiply both sides of AX equals B by orthogonal matrix Q, the norm of the error is the same as the norm of the original error. So multiplying by Q matrices doesn't change the least squares solution. So if you can reduce your AX equals B system down to row echelon form using Q matrices instead of M, then you can find the least squares solution easily then. Okay, the orthogonal matrices we're going to use, instead of pre-multiplying AX equals B, both sides of AX equals B by M matrices, we're going to multiply by these little Q matrices, which are orthogonal. Here's a typical one here, Q sub ij. The C and S are basically going to be the cosine and sine of some angle, but you don't really need to know the angle. All you need to know is that C squared plus S squared equals 1, so that this will be an orthogonal matrix. It's obvious that the rows are mutually orthogonal and have norm 1, so it's an orthogonal matrix. And we'll choose the C and S so that when we multiply A on the left by this Qij matrix, we will introduce a 0 in the subdiagonal element we want a 0. In other words, instead of knocking out A sub ij using M sub ij, we'll knock it out using Q sub ij. So when you multiply a matrix by Q sub ij with normal Gauss elimination, it only changes the jth row. It takes a multiple of the ith row and adds it to the jth row to knock out the element aij. Here you actually change both rows. You can see the new ith row is a linear combination of the ith and jth rows of A, and the new jth row is a linear combination of the old I and jth rows. And it's just a question of choosing C and S. Remember that C squared plus S squared has to be 1 for this to be orthogonal. It's a question of choosing C and S so that the element you want to be 0 is 0. And that's pretty easy to do, as we'll see in the following example. Suppose we want to minimize AX minus B, the norm of AX minus B. In other words, we want to make AX as close to B as possible in the L2 norm, where A is the 3 by 2 matrix shown and B is the 3 vector shown here. Basically, we want to reduce it to upper triangular form. That means we've got 3 elements to knock out, the 2 elements below the diagonal in the first row and the 1 element below the diagonal in the second row. So we've got to do 3 transformations. First, we choose Q21, we choose the C and S, so that after multiplying A by Q sub 21, the element 21 of A is 0, and it's just a question of writing out what the new element is and setting it to 0. In this case, C turns out to be 1 over the square root of 2, S is 1 over the square root of 2, and basically the angle is 45 degrees, although we don't need to know that. So we multiply both sides of our original equation, AX equals B. Of course, we know AX is not really equal to B, but let's say AX is as close as possible to B. Multiply both sides by Q21, and we get the system shown here. And notice we've knocked out this element. Now we knock out that element. It's entirely analogous to Gauss elimination. The only difference is we're using the Q matrices instead of M matrices. You can still think of basically we're taking using this diagonal element to knock out that one, except that they're changing each other. Both elements are going to change. Both rows, first and second rows, will change, but the net result is we get a 0 there. Then we knock out, to knock out this element, we use Q31, which is set up like that, that only changes the first and third rows. Notice it doesn't just change the third row, it changes the first and third rows, but the C and S are chosen so that the final result is a 0 here. And notice this stays 0 because we don't change the second row, only the first and third row. So again, it's almost exactly like Gaussian elimination, except that we're not exactly taking a multiple of the first row and adding to the third. We're replacing both the first and the third rows by linear combinations of the original first and third rows and doing the same thing to B. Then we've got one more step. We still got to knock this out, so we choose Q32 so that happens. And again, you can just write out what the final value is here and set it to 0, and it's easy to solve for C and S. So after 3 transformations, we now have it in upper triangular form, and we haven't changed the least squares solution. That is, the least squares solution of this problem is the same as the original one because we used Q matrices instead of elementary matrices. We used orthogonal matrices. So now it's easy to find the least squares solution because the last equation can't be satisfied no matter what x1 and x2 are. In other words, if you look at the vector ax minus b, the third component is going to be minus 1 over the square root of 6 no matter what x1 and x2 are. So we just give that up and choose x1 and x2 to satisfy the first 2 equations. That's just a question of back substitution. We get x equals 2/3, y equals 1/2, so that must be the least squares solution. Now, what is the QR decomposition all about? Well, as I said, that's basically the analogous thing for the LU decomposition for the least squares problem. If you want to solve another least squares problem with same matrix and different right-hand side, the QR decomposition is useful there. It's actually useful for some other things, such as finding eigenvalues. In fact, Section 3, which we're skipping in the Allen book, Chapter 7, talks about using the QR decomposition to actually find eigenvalues, but that we'll talk about in 660 if you're with us next semester. But let's just see what the QR decomposition is. Notice that just like in the LU decomposition, we multiplied A by Q matrices. We multiplied A by M matrices and reduced it to upper triangular form. Here we multiplied A by Q matrices and reduced that to upper triangular form, so that basically Q32 times Q31 times Q21A equals an upper triangular matrix, which for some reason is traditionally called R instead of U, but it's upper triangular, same as U. And the product of orthogonal matrices is orthogonal, so this is an orthogonal matrix. Let's call it Q transpose. Could call it Q, but I want to call it Q transpose. So basically, A pre-multiplied by Q transpose, which is really the product of those 3 little Givens rotation matrices, is equal to R. So that means A is equal to QR. So that's our QR decomposition. Notice we don't need to worry about pivoting here. There's no pivoting necessary with orthogonal matrices. Basically, if you have a 0 in the diagonal element, it doesn't matter. The Givens rotation will basically switch the rows for you. Okay, so now suppose you want to solve another least squares problem, AX equals D. AX as close to D as possible. Well, now that you know that A is QR, then you have QRX equals D, or RX equals Q transpose D. So you just have to multiply D by Q transpose, and then you solve this upper triangular system, again ignoring the rows you can't control and solving exactly to make the other component 0, so doing back substitution. So the QR decomposition basically serves the same role as the LU decomposition does, in that if you want to solve another least squares problem with the same right-hand side, same matrix, different right-hand side, you can do it quickly on the computer. Again, it may not seem any easier by hand, but if you're solving large systems, this is much faster because basically you've already got the decomposition of A in both cases.